A helium neon laser light with a wavelength of 632.8 nanometers is sent through two slits. The difference between the slits in length is 0.26 millimeters. At what position does the first maximum on the screen occur if the screen is 3 meters away? So they're saying that the length L is 3 meters. Pretty large distance between the barrier and the screen. The distance D is the separation between the slits, and that is D equals 0.26 millimeters. The wavelength of light, 632.8 nanometers. All right, the formula we want for this is this one right here. It tells you the position of a fringe. M is the number of the fringe that we're talking about. And it involves lambda, L, and D. All right, so we'll have Y M equals M lambda L over D, where M is the number of the fringe, which is an integer. All right, so M is 0 for the central maximum. M is positive 1 for the first bright fringe above the central maximum. So let M equal 1. So we're trying to find the position Y1 by plugging in which fringe it is. Plug in the wavelength. And the distance to the screen. And divide by the slit separation. You want to make sure to convert it to meters, of course. I get 0.0073 meters. What they're talking about there is this distance here. Okay, so this is called Y. And when you look at the interference pattern, you'll have your screen. It should be like this. Then it's dark. And then it's bright again. There'd be a bright fringe down here as well. This is the central max. First bright fringe. And this would be a dark fringe. Okay, so there's other things that we could be asked for as well. Like you might get asked for the angle that the fringe is at, for example. And there's a formula for that as well. The formula says theta m equals m lambda over d. Okay, now why is that theta so important? Well, we know that theta is this angle here, okay, but there's another theta, or another place where you can put it, and that's here. By geometry, they would actually be the same angle, the theta here and the theta here. So it's the angle that the fringe is at relative to the horizontal direction. So let's find that for the first maximum. All right, you just want to let m equal 1 again. And we can do theta 1 equals 1 times the wavelength and divide by the slit separation. And you get an angle, but it's going to be in radians, not degrees. I get 0.00243 radians. All right, not a very large angle. Now let's see what else we can find out about it. You might be asked, how large is the path length difference which is given by d sine theta for the first bright fringe? That's a common question. All right, so we would do this: d sine theta equals m times lambda. That's the formula for bright fringes. Okay, so what that means is that an entire wave has to be completed in that path difference so that when they come out, the waves are going to be perfectly in phase as they head toward the bright maximum. All right, so for the first, just let m equal 1. And so d sine theta has to equal 1 times the wavelength. Which is, of course, the wavelength. And that's how large the path length difference has to be for a bright maximum to occur. Now you can go to the second maximum, but in order to go to the second maximum, you have to let m equal 2 for the second bright fringe. And if that happens, we have to complete 2 whole wavelengths within that d sine theta path. It would now be equal to 2 lambda for the second bright fringe. And then, as you can see, when the waves emerge from there, they're going to be in phase. and we'll get that constructive interference on screen yet again.